To effectively address Heriot-Watt University Dubai's energy needs, we must first deeply understand our local climate. Drawing on data from sources like the Met Office and airport weather records, we see a distinct pattern: a hot, arid desert climate with two primary seasons. Summers from June to September bring extreme temperatures, often exceeding 40 degrees Celsius, coupled with high humidity. Winters from December to March offer mild temperatures, averaging 18 degrees Celsius to 25 degrees Celsius, and lower humidity. We experience minimal rainfall, typically 140 to 200 millimeters annually, mostly in winter, but with increasingly intense, albeit infrequent, rain events. Transitional periods bring temperature variability and potential dust storms. Critically, we enjoy abundant sunshine year round. This climate profile, with its intense solar radiation and high cooling demands, forms the basis of our energy planning. Given this climate analysis, let's explore our local resources for energy optimization. Dubai's intense solar irradiance makes solar energy our most promising asset. We can harness this through photovoltaic and concentrated solar power systems. Regarding wind, while not as consistent as solar, we must investigate higher altitude and coastal areas for potential wind energy generation. Detailed wind resource assessments are crucial here. The relatively stable ground temperature presents an opportunity for ground source heat pumps, offering efficient heating and cooling. Water, though scarce, can be leveraged through innovative approaches. We can explore using treated wastewater for cooling systems instead of potable water. Additionally, we must recognize that while desalination is energy intensive, powering these plants with renewable energy is critical. We must also acknowledge the urban heat island effect, where infrastructure traps heat. Keeping all of this in mind will influence energy demands and solar efficiency. Optimizing these resources requires careful logistical and technical considerations. For solar, we must identify optimal locations, such as empty areas, rooftops, and sites near existing electrical substations, to minimize transmission loss and land use impacts. For wind, detailed wind assessments and turbine selection for high temperatures and dusty conditions are essential. Ground source heat pumps implementation requires optimizing designs for our geological conditions. Water-based energy solutions necessitate pipelines for treated wastewater and cooling systems that handle high salinity. We must implement smart grid technologies to integrate intermittent renewable energy and develop robust energy storage solutions. Additionally, mitigating the effects of dust storms, salinity, and the urban heat island effect through advanced filtration, corrosion protection, and urban planning strategies is vital. In conclusion, by thoroughly analyzing the local climate around our university, we can strategically optimize our energy resources. Solar, wind, ground source, and water offer unique potential. By addressing the logistical and strategic technical challenges related to our environment, we can build a sustainable energy future. Let's commit to utilizing our local resources effectively, integrating innovative technologies, and implementing smart planning to ensure a resilient and prosperous future for the future students, staff, and faculty of Heriot-Watt University, Dubai.
Heriot-Watt University, Dubai, a building that is setting new standards in sustainability and energy efficiency. Opened in April 2021, this campus has already garnered significant attention for its groundbreaking features, making it the first campus in the UAE to achieve LEED Gold certification. This is a testament to its commitment to innovative building practices and energy-saving strategies. Heriot-Watt University Dubai's LEED Gold certification is the result of numerous sustainability measures incorporated into the building's design and operation. The building strategically maximizes daylight penetration, significantly reducing the need for artificial lighting. This not only lowers the energy consumption, but also improves occupant well-being. An impressive 94% of all equipment and appliances on the campus are Energy Star certified, ensuring optimal energy performance and lower operational costs. The building's lighting power consumption has been reduced by 34% when compared to ASHRAE standards baseline. This reduction is largely thanks to energy-efficient fixtures and automated lighting controls. Featuring double-glazed tinted curtain walls, the building reduces solar heat gain by blocking UV rays, helping to maximize the cooling load and maintaining a more comfortable indoor temperature. Data from DEWA meter readings were collected over a 12-month period from April 2021 to March 2022, and then extrapolated to provide an annual analysis. From this data, we observe some interesting trends. We see a significant spike in energy consumption in October, which corresponds with the start of the academic year when the campus is fully operational again after the summer break. A sample week from July shows that weekdays consume 6 times more energy than weekends, indicating the impact of campus activity levels on energy consumption. The campus's annual electricity load is projected to be around 3,268.7 megawatts per hour. This translates to 8.95 megawatts per day, which places it in the middle range when compared to other local universities. The building has an energy intensity of 161.4 kilowatt hours per meter squared per year, which meets the Econ 19 benchmarks but does not meet the SIPSI TM46 benchmark standards. This indicates room for improvement in energy efficiency. Energy consumption at Heriot-Watt University is primarily driven by space cooling, lighting, and equipment. Here's how the energy usage breaks down. The majority of the energy, about 70%, is used for cooling. Given Dubai's hot climate, maintaining a comfortable temperature is crucial for both the students and faculty. Efficient systems like fan cool units and chilled water system help manage this demand effectively. Lighting accounts for 15% of total energy consumption. However, with the use of LED lights and automated controls, this demand has been minimized. Electrical equipment, such as computers and lab machinery, accounts for 13.5%. Smart technologies like power strips and automated shutdown features help reduce this demand. The water heating systems contribute only 1.5% of the energy demand, thanks to efficient use of 5 strategically placed water heaters. The chilled water system, otherwise known as a CHW, plays a critical role in cooling the building. As expected, cooling demand increases in the summer months due to high outdoor temperatures, while it decreases in the winter months. During summer, from 15th of May to the 15th of August, approximately, chilled water consumption rises as depicted in the graph. This is when the demand for cooling peaks due to higher temperatures. In winter, from 1st of November to the 1st of March, chilled water demand drops as cooling needs are reduced. However, the system is still actively used to maintain air quality and comfort levels.
Hello, my name is Ms. Today I'll be presenting a comprehensive analysis of water demand of our university, Heriot-Watt University, over the course of a year. This analysis focuses on how water is used and how consistently it is used, and tells us about operational efficiency across the campus. First, we look at the water demand. We started by estimating the usage daily water consumption for each month from April 2021 to March 2022. These values were shown from visual graphs that show daily water usage pattern and were then multiplied by 30 days to give us a monthly estimate in kWh. For example, in April, average daily water use was 5.0 kWh, given monthly of total of 150 kWh. In comparison, November saw the highest usage with 7.0 kWh, total of 2.10 kWh. These values reflect the typical academic calendar, with lower usage in April and August, likely due to breaks, and higher demand in November and March than because the university is the busiest by these timings. Then we look at the load factor, and the way we found and calculated load factor is by the formula of load factor equals average daily consumption over peak daily demand. We assume a constant peak demand of 50 kWh. From that, calculated the load factor from each month. For example, April had the load factor of 0.100, meaning water use was very inconsistent, likely due to the breaks, minimal campus activities. In September, it improved to 0.130 as students returned and the university became busy again. November had the highest load factor of 0.140, indicating the most consistent, effective usage across the month, likely because of steady academic activities. Then we move to the university facilities water demand. Here we created this graph to better understand where the water goes. We created an estimated breakdown by facility type based on typical campus infrastructure. We assumed the wet labs were about 30% of the total water due to the cleaning, rinsing, and lab work, while we also had the free water dispensers up for 25% used by student staff throughout the day. Water heaters, including kitchens, bathrooms, were estimated at 20%. Water fountain, which is placed at the ground floor, took 15%, and the cleaning and maintenance took up to 10. This all adds up to 100 and helps us visualize where the most, how the water is moving and how the system improvements could have the biggest impact. To calculating the hot water demand. From the water heater, we made a conversation of estimating of hot water demand. We assume that only 20% of the water flowing through the heaters is actually heated and used as hot water. That leads us to this calculation, which is hot water demand is equal to 20 times 20%, which will equal 4%. So based on this calculation and formula, we found out that it's only 4% of total hot water usage.
This part of our video looks into our recommendations for different on-site energy generation methods. The first goal was looking into electricity generation technologies, considering our university's ample supply of sunlight by installing photovoltaic panels. After a critical analysis of the different types of PV panels, we went ahead with a hybrid system of monocrystalline and bifacial solar PVs. Having bifacial on the parking, which has a high efficiency and can help generate 25% more energy than normal panels with a durability of over 25 years. A total combination of 214 panels were installed facing the south at 22 degrees on the roof as well as the parking shade. Another recommendation for additional electricity supply was to consider the possibility of an adaptive solar facade in replacement of the existing louvers to increase the building's energy efficiency. With an analysis of the solar facade, which is an advanced facade system designed with thin films photovoltaic panels that have soft pneumatic actuators for solar tracking and daylight management, which allows the university to maximize solar efficiency through zone tracking while limiting solar gain from entering the southern facade of the building. This could be done with a photovoltaic envelope that uses lightweight solar panels and robotically controlled actuators to actively follow the sun and create electricity, while also acting as a thermal barrier to enhance the university's internal atmosphere and make it comfortable for its occupants. The monocrystal panels combined with the solar facade supply 114.1 megawatt hours of energy per year with a payback period of 8.5 years.
Hey, I'm Wala, I'm going to talk about solar heating. Heat pumps use ambient air as a renewable heat source, delivering 3 to 5 times more heat than the electricity they consume. They integrate with solar PV for low-carbon solutions, but are less effective in extreme cold and require large outdoor units, which need careful placement. Solar thermal heating, which is the recommended option. Solar thermal heating is ideal for today's climate, efficiently heating water while reducing energy demand in university buildings. It works well with HVAC systems, lowering heating costs, although it requires rooftop space and has a high initial investment. It offers a long-term savings. So if you compare between solar thermal air source heat pump gas boiler, we can find that solar thermal is highly suitable for an university. This series of glass tubes to capture the sun's energy and transfer it to a special collection manifold. Inside the glass tube is a small copper pipe filled with a special heat-sensitive liquid. The liquid quickly turns into a hot gas which travels the tube into a collection bulb. So whenever the sun is in the sky, the tubes will capture the sun's energy. Water is then pumped around the bulbs to heat the water and then down into the tank to be ready to use. Evacuated tube collectors and flat plate collectors, both of them aim to heat water sustainably, but their efficiency and practicality differ. We compare them based on heating capacity, efficiency, power needs, cost effectiveness, and integration. Evacuated tube collectors offer higher efficiency than flat plate collectors, perform well in cloudy weather, and require less roof space. However, they come with higher upfront cost and more complex maintenance. Despite this, their superior performance make them a strong choice for sustainable water heating in diverse climate. Solar collectors, pump station, expansion tank, differential controller, hot water storage tank, and backup heaters such as a boiler or tankless water heater. Energy from the sun transferred through the glass of the collector and is absorbed by a component called an absorber plate. The absorber plate has a special coating that is designed to capture as much solar energy as possible and converts this energy into heat. The heat is then transferred to a fluid passing through multiple small pipes attached to this absorber plate. The solar heated fluid is pumped down to a storage tank where it's circulated through a coil of pipe called a heat exchanger. This is how the heat is transferred from the solar heated fluid to the university. Now, once the hot water tank reaches its maximum temperature set point, the solar differential controller turns the pump off until the tank temperature drops again. This cycle continues for as long as solar energy is available. Now let's say we have a couple of cloudy days in Dubai. Does this mean we have to suffer through the cold water? Absolutely not. All solar hot water systems have a backup heater, so we can use hot water even in the cloudy days. To meet Heriot-Watt University Dubai daily hot water demand of 40,000 liters, we calculated the energy required using the heat capacity of water. The result is approximately 1,628 kilowatt per day. Considering a 60% efficiency rate, the actual energy need raises is 2,714 kilowatt per day. Given solar panels provide around 5.5 kilowatt per square meter daily, we determined that 494 square meters of solar collectors would be required to sustainably meet this demand.
Wind energy generation was the use of the vertical axis wind turbines, which are ideal for urban environments due to their ability to capture wind from all directions. These turbines utilize vertically mounted blades connected to a central shaft. When wind flows across the blades, it causes rotation that activates a gearbox in the generator, allowing electricity to be produced efficiently even at low wind speeds. A total of 68 vertical axis wind turbines were strategically installed on the rooftop of the university. The compact design of each turbine, measuring 3 meters in height and 1.5 meters in diameter, allowed for high-density installation without interfering with existing building systems or rooftop equipment. These turbines provide a clean and renewable source of energy with minimal noise and carbon emissions, supporting the city's goals for sustainable development and reduced dependence on fossil fuels.
Humans have been utilizing water to get work done since ancient history. The earliest use of water for power was during the Han Dynasty between 202 BC and 9 AD by using trip hammers powered by a vertical water wheel to pound whole grain and to break ores. Hydropower has evolved significantly since then, and today it is a crucial source of electricity for many countries. Hydropower accounts for 71% of all renewable electricity, making it the largest source of renewable power in the world. It is a clean and sustainable energy source that plays a vital role in reducing greenhouse gas emissions and combating climate change. There are three main types of hydropower generation: run-of-river, storage, and pumped storage. Run-of-river hydropower redirects water flowing in a river through a canal or penstock, which then spins turbines to generate electricity. Storage hydropower involves storing water in a reservoir and releasing it through a penstock to generate electricity. Pumped storage hydropower is a system of two water reservoirs at different elevations, where water is pumped to the upper reservoir during low demand and released to generate electricity during high demand. Each type of hydropower has its unique advantages and applications.
In conclusion, Heriot-Watt University Dubai has made significant progress in sustainability with its LEED Gold certification and energy efficient systems. Let's see the energy demand reduction and the integration of renewable energy sources. With the addition of PV panels, they could generate 241,400 kilowatt hours per year, reducing reliance on grid power, especially during peak daylight hours. And with the addition of wind turbines, they could contribute 31,824 kilowatt hours per year, diversifying their renewable energy mix. By incorporating solar and wind energy, the university's total energy demand would drop from 3,268,672 kilowatt hours to 2,995,448 kilowatt hours per year, cutting 273,224 kilowatt hours. This shift reduces both operational costs and campus's carbon footprint, making the university a leader in sustainable practices in the UAE.